Hello students, this is Chintan Patel and welcome back to the video lecture series of the fundamentals of machine design. Well, in this video we are looking at the notes of the chapter number 1, that is basics of the stress and the strain, and the part 3 of the note is going on in this particular video, which is nothing but the elastic constant. The part 1 and part 2 was already covered in the previous video, so if you haven't seen it, then go check out that videos from my playlist. Now this is the part 3 of this particular chapter number 1. I am going to provide the download link of this particular PDF in the description of this video, so that you can find that link and download the notes from the description. And this is the final topic of this chapter. It will help you to understand the concepts of this chapter and as well as the examples before going for the examination. To quick revision, this note can be useful. So basically we are starting our lecture from the basic concepts which were already covered in the previous videos, and that's why we are going quickly so that we can cover it within the stipulated time. First one is the linear strain. Linear strain is denoted by the epsilon. Whatever the strain that we have calculated up till now in the part 1 and the part 2 are the linear strain. There is another strain which is termed as the lateral strain, and lateral strain is denoted by epsilon dash. There is a dash on the top of the epsilon. Okay, so basically the linear strain and the lateral strain, the deformation per unit dimension is called as a strain. This is the normal one which we have already calculated. Okay, there is no difference between the previous strain and this one. We have just represented or denoted it with the new name, that is the linear strain. So the equation, as you can see, is also the same, that is delta L upon L. Now consider a body. Let's say there is a body which is already drawn in the below diagram. As you can see, let me explain it this way. As you can see, there is a body which is having a cylindrical shape. If you pull this body and try to elongate its length, then the length will be increased, but if you consider the final diagram, then the final diameter of the cylinder will be reduced from the original one. So original diameter was D and the final diameter was D dash. Okay, so as you can see, the diameter is changing, and as the volume of the body is the same, and that's why if the length is increasing, diameter is decreasing. So we can consider that if the linear strain is positive, the length is, if it is increasing, then the lateral strain might be reducing. Okay, because the volume of the body is constant. So this may be occurring in the case of the linear and the lateral. So you have to keep that in your mind, because these concepts are going to be introduced in the case of the examples. In the examples, you will have to decide which strain is positive and which strain is negative. You will have to think on your foot that as the length is increasing, the other dimension might be decreasing, and that is why we will take that particular decreasing dimension in the negative note. Okay, so you will have to take some, you will have to use some of the common sense so that you can easily denote a plus or minus sign into your examples. Okay, so particularly the lateral strain is the change in a dimension on the other side, or we can say that the perpendicular to the original dimension. If you consider this dimension D, so the dimension D can be measured, dimension D can be measured vertically, and the length is measured horizontally. So both the directions are perpendicular to each other. So the dimension which is perpendicular to each other, or we can say that the transverse dimension, transverse itself indicates that it is perpendicular to the previous one. Okay, so the to the transverse to the linear strain, it is called as the lateral strain. So this is the another type of the strain which we will be using for the calculation of the example. For the rectangular bar, lateral strain can be denoted as the delta B by B as well as the delta A by D by D, whatever the dimensions of the lateral in the lateral direction or the transverse direction. There might be different types of the lateral strain available in the case of the rectangle. So we will see different types of the cases over here. As you can see, this is our rectangle. The lateral strain which are in the lateral directions. So we will consider the direction of the length as the direction of the axis. So this is our axis, okay, in the z direction, and perpendicular to the axis there are two different directions. The first one is the vertical and second one is the horizontal. Okay, so these two are perpendicular to each other. Okay, this one is perpendicular and this one is perpendicular. So as you can see, in the horizontal direction there is a dimension called as a B. Okay, so this is also a lateral dimension B, and in the vertical direction there is a dimension T. This is also a lateral dimension. Okay, so this is our linear dimension, that is L. Linear dimension L in the direction of the axis, lateral dimension B and T perpendicular to the axis. Okay, so you should remember like this. Okay, so change in thickness or change in width upon original thickness and original width will give you the answer of the lateral strain. Okay, so lateral strain could possibly be there will be two lateral strain in the case of a rectangle, lateral strain for the width and the lateral strain for the thickness. Okay, so another term which was introduced in our videos were the Poisson's ratio. Poisson's ratio can be represented by mu or 1 upon m. Both are the same, both are the symbols used to denote the Poisson's ratio. What is Poisson's ratio? It is ratio of the lateral strain upon linear strain. Lateral strain can be represented by epsilon dash and linear strain can be represented by epsilon. So mu is nothing but the epsilon dash upon epsilon. So you should remember this equation also, because it will have a tremendous amount of the use in our examples. Okay, so basically this is of very useful. Generally not every time. Generally the mu will comes within this range, that is 0.25 to 0.42, but in some of your examples the mu may be larger than the 0.42 and may be smaller than the 0.25. So mu generally comes into the range of this much, but it is not necessary. Okay, the volumetric strain. Volumetric strain is our next topic. So volumetric strain is, as the name itself suggests, that it is the change in volume upon original volume, just like the linear strain, just like the normal strain. Okay, so volumetric strain is nothing but the change in volume, that is delta V by V. Now we will see another topic, and that is nothing but the volumetric strain of the rectangular body subjected to an axial force. Now you must focus on the particular words. As you can see, there is only one force which is acting axially. There is only one force, an axial force. That means there is only one force which is acting in the direction of the axis. So this is the direction of the axis. Which is the direction of the axis? Axis will always be considered along the largest dimension of the body. So what is the largest dimension of the body over here? The length is the largest dimension, and the width and thickness are smaller than the length. That's why we are considering the direction of the length as the direction of the axis. So this is our axis, and along the axis we are applying the axial force P. This is axial force P. Okay, so as this force is having the nature of the tensile nature, that's why the body's length will be increased, but the volume is the constant, so width will be reduced as well as the thickness will be reduced. You should keep that in your mind. Okay, so first of all, linear strain, that is epsilon 1, is nothing but the sigma upon E. Okay, so sigma can be calculated by this equation, force upon area. But which area should be considered? We must consider the cross-sectional area which is perpendicular to the force. Now the area which is perpendicular to the force is this one, and this area can be calculated as the B into T. Okay, so this is our area B into T. Okay, so if you put this value of the area in our equation, then you will calculate the answer of the sigma. From sigma you will be able to calculate the strain. This was the linear strain. Now the lateral strain. Lateral strain and linear strain are connected together with the Poisson's ratio, because Poisson's ratio is nothing but the lateral strain upon linear strain. So in order to calculate the lateral strain, we will use the Poisson's ratio, this one. And we know that the lateral dimensions will be reduced, because if the length is increasing, width and thickness will be reduced, and that's why we are using the minus sign over here. Okay, minus sign is the indication that your lateral strain is for the reduction. Okay, your strain is for the reduction. So basically we have used a minus sign over here. And if you put the volume equation of the sigma epsilon 1, then your final answer comes out to be the sigma upon me. We also written over here that is it's of a compressive nature, because the minus sign itself indicates that it is reducing, and that is why we have written in the bracket that's the compression. Now volume of the body can be written as the LBT. And if you partially differentiate, if you differentiate it partially and divide it with the volume, then you will get this equation. Differentiate partially, that means delta V, delta L, delta B, delta T, and the rest of the parameters will be the constant. If you divide it with the volume, then you will get this equation very easily, okay, on the simplification. And this equation is for epsilon V, that is nothing but the volumetric strain. This equation is for the linear strain. This one is for the lateral strain. This one is also for the lateral strain. So that's why we have written it like this. Now if you put the value of the linear strain like this, lateral strain like this, and lateral strain like this, and simplify this equation by taking the sigma by E as a common, then the rest of the equation would look like this, and that is our final equation for the example point of view. So this is our final equation for examples. You need to remember this equation when in your examples they are asking you to find out the volumetric strain for a rectangular body or cylindrical body. It is also applicable for the cylindrical body when the body is subjected to only one axial force. Okay, only one axial force is there, then you can apply this equation directly if you remember it. Okay, so this is applicable not only for the rectangular body, it is also applicable for the cylindrical body. So we will see another equation in the upcoming page. Volumetric strain of the rectangular body subjected to three mutually perpendicular forces. Now as you can see, there are three different forces acting on the body, and for these three particular forces, each force will have each strain value. As you can see, X force, Y force, and Z force, and summation of all these forces will give you the answer of the delta V by V. And the answer for this type of equation can be derived using the same method that we have used in the previous derivation. And if you simplify it, then you will get this equation directly. The derivation of this particular equation is not generally asked in your examination. If it is asked, then you can derive it using the previous method, but it is not asked. That's why we are remembering the final equation only. Okay, so you should keep that equation in your mind while solving the example, so that it will be handy for you to solve the examples. Okay, so basically we are going to move on, and we will see another definition, that is the bulk modulus. As you can see, bulk modulus can be represented by the K, that is the denotation, and the bulk modulus is the ratio of the direct stress upon volumetric strain. Now there is one condition in the case of the bulk modulus, that there will be three mutually perpendicular forces acting on the body. There will be three mutually perpendicular forces acting on the body, and those forces will be having the same intensity, or we can say that those forces will generate the stresses, and stresses will have the same intensity. So the three mutually perpendicular stresses are subjected on the body, then you can calculate the value of the bulk modulus, and that is the direct stress upon volumetric strain, and which can be calculated using this formula, that is the sigma upon epsilon V. Now another question which is generally asked in your examination, that is the relation between those elastic constants, and that is also very important question which can be asked repeatedly in your GTU, and that is why the relation between the E, that is Young's modulus, K, that is bulk modulus, and mu or 1 upon m, that is the Poisson's ratio. So relation between those elastic constants can be asked, and this will be derived in the upcoming pages, as I am not going to explain the entire derivation over here, because the entire derivation was explained in the previous video of our Earth. So if you haven't seen that video particularly, then you can go back and check our playlist, because this entire entire derivation is covered in particular that video. Okay, so if you want to have a note, then you can download it and you can watch the easiest method to derive this particular relation. Okay, so I'm going on further. As you can see, this is the same method or the same steps which we were used to derive that particular equation, and the relation between those elastic constant will be like this one. So K, that is the bulk modulus, is equals to m into E upon 3m minus 2. 3m minus 2. Now here m is nothing, 1 upon m is mu. Okay, 1 upon m is mu or the Poisson's ratio. M is not the Poisson's ratio. 1 upon m is the Poisson's ratio. Keep that in your mind. So whenever in your examples they provide you the Poisson's ratio, then don't put that Poisson's ratio value directly into the m. So convert it into 1 upon m, then you will write the value of the Poisson's ratio, whatever is given in your example data. Otherwise your answer will be wrong and you will get no marks for that particular wrong explanation or the derivation. The next one is the shear stress. Now shear stress is another type of the stress. As you can see, it is the we have seen normal stress so far. Normal stress is the stress where the force is perpendicular to the cross section area. Now we are looking at the shear stress. Shear stress will be applicable in the case of the fluid mechanics also. Okay, so shear stress is generally a stress which is generated due to the force which is applied parallel to the cross section area, or if your resisting area, or if we can say that the braking area is parallel to the direction of the force, then that type of a stress will be generated like a shear stress. We have taken an example of the rivet over here. As you can see, there is a rivet. So this one is our rivet. If this rivet is used to join the two different plates like this, okay, and if we apply the pull force on this place like this and this place like this, then the rivet will be under the action of these two forces. So let's say the rivet is failing, rivet is breaking. What is the maximum possibility of breaking the rivet is over here. The rivet will try to break from here. Okay, so this is the breaking point of the rivet, or it will break from the horizontal cross section area. As your breaking area is horizontal, your cross section area is horizontal, your force is also horizontal, so both are parallel to each other, then that type of a stress is known as a shear stress. In the case of the normal stress, in the case of the previous stress that we have already studied in the previous parts, then there was the breaking area which was generally vertical and force which was applied was horizontal. Both were perpendicular to each other, and in this particular stress both were parallel to each other, and that is why this type of stress is named as a shear stress. So basically shear stress can be calculated using the same equation, that is the shear force upon shearing area. Shearing area is the area from which the body is breaking, or from which the body is offering the resistance, or we can say that it is the area parallel to the force. Okay, so this is the shearing area or cross sectional area, also named as a cross sectional area. So basically force upon area is known as a shear stress. Shear stress can be denoted by the tau. Till now we have used the tau to represent the torque, but from now we will use tau to represent the shear stress. Up to the 8th semester you are going to represent the shear stress by the tau, nothing else, and the torque will be represented by the capital T. Okay, so this was the shear stress, Newton per mm square. Okay, the modulus of rigidity, is coming from the shear stress only. So modulus of rigidity can be represented by the C or N or G. There are three different names or notation to represent the modulus of rigidity. What is modulus of rigidity? It is nothing but the ratio of the shear stress upon shear strain. Shear strain is represented by the phi. Okay, so tau upon phi is the answer of the modulus of rigidity. Now modulus of rigidity is generally denoted by G, but it can be denoted by C or N. So relation between the modulus of rigidity, modulus of elasticity and Poisson's ratio can be written like this. There is also a relation or the derivation for this particular relation also, and it can be found in your notes as well as in your textbook, which is same as we have studied in the previous lectures. Okay, so we will move on to our next topic, that is still punch. Now this is the type of example which can be asked in context of the shear stress. As you can see, the still punch is used to create the hole, and after creating the hole, this is our punch which is left out of the hole. So the material is failing from here. If you consider it is the vertical or the circular portion which is in the vertical direction, okay, and you are applying the force which is also in the vertical direction, that's why the shear stress will be generated. But basically you are applying the force on the plate, and the plate area is horizontal, you are applying the force vertical, that's why it is also a normal stress phenomena. But after, when it breaks, then at the time of a breaking, that breaking is known as a shearing phenomena. Okay, so it is a combination of both the stresses. So first of all, we are considering the compressive stress. Compressive stress can be easily found using the force upon area, that is the P by A. Area is nothing but the pi by 4 d square, and the shear stress can be found using the shear force upon area. Now what is the area? Area is the parallel to the force, which is the surface of the cylinder which is cut out from the hole. Okay, so this is our cylinder, and the surface of the cylinder can be calculated using the pi dt. That is our area. Now if you compare both the forces, compressive force and shear force, you will get the answer whatever you need to calculate from the example which is asked in your examination. So this is the basic idea of the still punch, which you need to remember in your mind, because the example of the 3 or 4 marks may be asked using this concept, and that is why we are moving on right now. Let's look at the examples. Okay, so first of all, a data is written over here, that is the rectangular block of the size 300 by 150 by 100 mm. So the size of the rectangle is provided. The 300 is the length, 150 is the width, and 100 is the thickness. Okay, so we have written 300 over here. This is our 300. This is our 150, and this one is the 100. That is thickness. Although it doesn't look like a 300, 150 and 100, but we have mentioned it like that. Okay, you don't have to just scale it using the scale. You can directly draw whatever you want to draw. Okay, any diagram with the free hand is acceptable. Now we will move on to the next thing. Next data which was provided is subjected to a forces as shown. If the Young's modulus E is the 75 gigapascal, Poisson's ratio is 0.25, calculate the change in volume G and K. These things are asked. Change in volume can be found using the equation of the volumetric strain. Volumetric strain is nothing but the change in volume upon original volume. So if you can find out the change in volume, if you can find out the volumetric strain, then multiply it with the original volume and you will get the answer of the change in volume. So basically we are looking at the solution of the volumetric strain. In order to find out the volumetric strain, you must decide which case is it. Is this the case where only one force is applied? This is the case where 3 different forces are applied. So those 3 forces are also in a mutually perpendicular direction, and that is why you will have to use the equation number 2 that was derived from the previous session. Okay, that was derived in the previous pages. Okay, so for that particular equation, you will need sigma x, sigma y and sigma z. Basically, we don't know which one is the compressive and which one is the tensile. You will just have to look into the diagram. As you can see, this one is also tensile, this is also tensile, and this one is also a tensile. Each and every forces are of the tensile nature. That's why you don't have to worry about the plus or minus sign right now. But if one of the forces is a compressive, then you will have to use the negative sign for the compressive force, because it will try to reduce that particular dimension. And that is why you will have to keep that in your mind while dimensioning or denoting the sign for the particular stresses. Okay, so this is the tensile stress. That's why we have taken it as a positive. Another tensile stress in the y direction. Y means the vertical direction, z means this direction, and stresses can be found using the force upon area, basic equation, force upon area. And which area we are considering? The area which is perpendicular to the force. Let's say if we are talking about the 150 kilonewton force, okay, 150 kilonewton force. Where is 150 kilonewton force? This one. If this is the 150 kilonewton, the area which is perpendicular is this one. Then you need to put this area into the equation over here. Okay, so we have written 150 into 100. So if you are talking about a 225 is over here. Okay, so this is our 225. So perpendicular area will be like this, and you will have to write this area over here. Okay, so this is how we are going to calculate the three different stresses. Now put all this value into the equation that we have already discussed in the previous session. That was the equation like this. Where sigma x upon E minus sigma y upon E and sigma z upon E. If you take 1 upon E as a common, then you will simplify this answer and you will get the answer in terms of the E. Now we know that we need to calculate the strain, because ultimately we are requiring to calculate the value of the volumetric strain. So basically this is not the sigma x, this is the epsilon z. Okay, so what we are trying to do right now here is we are trying to calculate this epsilon x, epsilon y and epsilon z. So this is a printing mistake, writing mistake, whatever you consider. This is not the sigma, this is the epsilon. This is epsilon z. Okay, so epsilon z is calculated over here, the same method, and if you put all this value into this equation, you will get the answer of the delta V by V. But our intention is to find out the delta V only. That's why we are going to multiply the V, cross multiply the V with the original answer, and we will get the answer of the delta V as a 690 mm cube. Be careful while writing the units. Right now we are going to move forward. Another thing that they have already asked is the value of the G. G can be calculated using the relation ME upon 2m plus 1. If you know this relation, then you will be able to put all this value which are already provided, which is already available, and you will be able to calculate the answer of G. Similarly, if you want to calculate the K, then use the relation of the K and put all the value which is already available and calculate the answer of the K. So this was the end of our example. The another example is also provided in our notes, and this is nothing but the example which was already discussed in our previous videos. So if you haven't seen that example, you can go check back to our playlist and check out this example explanation. So this was the end of our part 3 of the notes. This is how I end the chapter number 1, that is the basics of the stress and the strain. It consisted of the 3 different parts, that is the simple stress and strain, simple stress and strain, elastic constants, and thermal stress and strains. So all the parts of the chapter number 1 are covered, and you can consider this handwritten notes, or you can download this handwritten notes from the description of this video, and keep practicing, keep learning, and we will meet in the upcoming videos of the chapter number 2 notes, as well as the chapter number 2 topics and examples. Till then, thank you.